Thank you very much, Uri, for thank you for inviting me, for putting on this amazing meeting, and for your vision. It's a very ambitious, exciting vision for optometry and vision science in Israel. So in advance of our collaboration, which I think we're all looking forward to, Dean Flanagan and myself, and I think everyone at Berkeley, very excited about this. Uri asked me to give a brief description of the Vision Science graduate program in Berkeley as a potential model for Bar-Ilan. And it is an interesting possible model because it's an interdisciplinary program. As Uri already told us, vision is complex. It involves the eye, it involves biochemistry, it involves anatomy, physiology, stem cells, it involves neural processing, it involves brain mechanisms. And really the only way one can tackle a subject that's that vast is through an interdisciplinary program. And so the Vision Science Graduate Group in Berkeley is such a program. It's now more than 70 years old. And it was part of the original mission of the School of Optometry, which itself was a part of the physics department back in the olden days. And currently we have 32 faculty members in vision science, 38 graduate students. The program has graduated more than 240 students and trained numerous postdocs over the 70-odd years that it's been in existence. And not that we're biased, but we think this is the #1 vision science program in the world. It's certainly the largest, and it's the most comprehensive because it does involve people from so many different departments. The researchers, the faculty have on the order of $13 million a year in grant support. We're all praying that in Trump world it will continue. We're not sure. We'll see how that goes. We have 40 NIH research grants. We have a core grant that provides a variety of research services in microscopy, in helping with clinical trials, in computer programming, in optical imaging, and so on. And we have a training grant support for more than 40 years. We're just applying now for the next 5 years of support. And this program, this training grant, supports 10 PhD students, provides their tuition and their stipends, and it also supports several postdocs. We have a K-12 grant. This is a mentored clinician scientist grant that we bring in optometrists or ophthalmologists or even veterinary surgeons who want to learn to do patient-based translational research, and they are supported by this grant. I think we have 7 or 8 of those trainees. And we have a summer research grant that puts a dozen optometry students into labs during the summer and pays for them. This is a map from overhead of this is a view from overhead of the Berkeley campus. This is the football stadium. It's always a very big deal on American campuses. This is the School of Optometry here, which is sort of the center point of the Vision Science graduate program. It's the host. But the faculty and the students live in all of these different satellites. These are departments such as psychology, computer science, bioengineering, molecular and cell biology, neurobiology, the Helen Wills Neuroscience Institute, in School of Public Health and Epidemiology, and of course in optometry. And so graduate students work with faculty in all of those units, but are part of the Vision Science program. And they're bound together by weekly seminars, by a core set of courses that gives every student a kind of basic, the fundamentals of vision science, what every vision scientist should know about the eye, about visual processing, and so on. That's about a year's worth of courses. We think about our research in sort of 6 diverse areas: biomedical optics, computational vision, molecular and cell biology, neuroscience and neurobiology, perception and cognition, and clinical science. The School of Optometry, which plays, of course, a large role as the host of the Vision Science program, has a very busy clinic. Some 80,000 patients a year visit the clinic, and there's a translational research center which provides opportunities for clinical trials. So another way that we sort of think about this multidisciplinary approach is that we have people working in optics and refraction, clinical eye disease, action and eye movements, molecular biology and genetics, computational vision, perception, psychophysics, neuroscience, and so on. And this is just a partial list of the faculty in these different areas. And I'll just mention a few bits of the kinds of research that goes on. Austin Roorda works on adaptive optics, so he uses adaptive optics in the same way that if you want to see distant stars or planets in a murky sky, astronomers use adaptive optics to essentially measure and correct for the turbulence in the atmosphere. The eye has got cruddy optics. It's, you would be upset if you bought a camera that had optics as poor as the human eye. And so what Roorda does is use these methods of adaptive optics to measure the aberrations of the eye and correct them on the fly. And so you can see when the correction comes in, you can see now blood vessels, you can see individual photoreceptors, all those dots. You can put images on the retina directly and visualize precisely where they are. And because the system acts as a scanning laser ophthalmoscope, you can actually stabilize the image on the retina with an accuracy that's smaller than a cone in the retina. They've used this method to study single units in the lateral geniculate nucleus as well. Another lab, Chris Wilson, works on myopia, particularly using chickens as a model. There are labs that are interested in doing realistic rendering, in providing better ways of treating, of correcting vision in people who have keratoconus, who have corneas that are very distorted, with Jitendra Malik in electrical engineering and computer science, who does object recognition using computer vision. We have people working now on autonomous cars. The Shore Lab works on accommodation. There's a lot of work going on trying to develop intraocular lenses that focus. And eye movements, we have a number of people working on attention and the visual aspects of attention. Jack Gallant's very involved in trying to decode vision by using functional brain imaging to essentially read your mind. We have the Redwood Center run by Bruno Olshausen that does a lot of computational modeling of human vision. Marty Banks works on how the brain combines visual and tactile information and display technology. And then we have a number of labs like Marla Fellers, who looks at the development of functional circuits in the retina. Rich Kramer's lab, they're developing methods for optically controlling neural activity, kind of optogenetic methods. And our most recent acquired faculty, Roland Taylor and Teresa Putiseri, looking at retinal neurobiology and neurophysiology. John Flannery is using virus vectors to deliver therapeutic genes and other payloads to retinal cells. Zhao Gong's lab has discovered many of the genetic mutations that mimic human clinical eye disease. Lu Chen works on the lymphatic system, which turns out to be a very important player in wound healing in the cornea. Carson Gronert works on lipid mediators. We have people working on infectious eye disease and diabetic retinopathy and on children's vision. And so we have a really broad array of different kinds of research. Our students, I should just mention, back in the olden days, the students really trained for a career in academics, and that's pretty much what they did. We're preparing our renewal of our training grant now, and we're looking back at the last 10 years, what happens to the students, and it turns out more than half of them are going into industry and high tech. My most recent PhD student just joined Apple. We have students working at Facebook, at Oculus, at Microsoft, at various other high-tech industries and biotech industries. So I think there's a rich array of options for students in this kind of a program beyond just the academic lab. So that's about what I wanted to say about the program. The interdisciplinary nature of it, I think, lends itself very well to Bar-Ilan with its excellent, various excellent departments. And so from now, I want to talk a little bit about my own work we've been doing recently on learning to see in depth. So we'll start off with this nice quote from Eleanor Gibson about learning, and perceptual learning in particular. And she said that perception is educable is clear from many real-life instances. A butcher can heft a piece of meat and estimate its weight with great accuracy. The physicist Michelson became so skilled at estimating the degree of distinctness of the fringes of light waves that these visibility ratings permitted him to compute the nature and shape of the spectrum lines. We typically use a much narrower definition of perceptual learning, which is that in normal adults, if you perform a challenging visual task, something that pushes you to your threshold, you can improve through repeated practice. And people with normal vision can improve their vision in a wide range of tasks, such as orientation discrimination, spatial frequency discrimination, texture discrimination, Vermeer acuity, and so on. And this perceptual learning reflects a vast network of neural substrates. And so this is just one example from a recent paper, not so recent, by Schwarzkopf and Kurtzi, showing many areas of the brain that are activated through perceptual learning. That is, before learning, they're not active. After learning, they are active. Okay, sorry about that. So people with normal vision can also learn to see in depth by practicing. And the thing that I'm particularly interested in is learning depth perception based on stereopsis, which is the impression of three-dimensionality that we get, of objects popping out in the world in depth, that we get because we view the world with two eyes that are separated laterally in the head, and that provides us with this binocular disparity, which is the difference between the two retinal images of the same world. Why does stereopsis matter? Well, I'm going to try to show you this movie. Turns out that if you have to pick up a peg from a board like this and place it in a tray, it's much more difficult to do with one eye than with two eyes. That's what the movie would have shown you. And this is some data from Preeti Verghese showing that the binocular monocular placement time, the time it takes to place the peg. Okay. If monocular and binocular are the same, the ratio would be 1. If binocular with both eyes is slower, you get numbers above 1. If binocular, both eyes is faster, you get numbers below 1. And what you can see is that the better the stereo acuity, people with good stereo show a large binocular advantage. And people with poor stereo, and particularly this group of patients up here who have low vision, who have macular degeneration that's different in the two eyes, so the two eyes don't work together, get essentially no advantage. So stereopsis matters in normal binocular vision because depth thresholds are about a factor of 10 better than monocular thresholds. And visually guided hand movements are significantly impaired when viewing is restricted to one eye. And this binocular advantage is highly correlated with stereo acuity. This article appeared as an opinion in the New York Times a couple of weeks ago. It's written by Howard Axelrod, who lost his right eye playing basketball in an accident. And he says, depth perception depends on binocular vision. The brain needs information from both eyes to coordinate where objects are in space. Without depth perception, I often stumble on stairs and curbs and sudden drop-offs, like sunken living rooms. They greet me with a jolt. And for normal stereopsis, the two eyes have to work together. They have to be aligned. They have to be functional and reasonably well matched. There has to be neural control over the eye muscles and the vergence to bring the two images into alignment. The images in the two eyes have to be pretty well matched, and there needs to be a neural mechanism to combine images from the two eyes and compute depth from binocular disparity and combine it with other cues. And many areas of the brain are activated by binocular disparity. This slide just illustrates that areas that are lit up by binocular depth. But not everyone can experience stereopsis. And the estimates range between 5 and 20% of the population that are stereo blind or stereo deficient. There are a wide range of causes of stereo deficiency. Parietal cortex damage leads to the percept of a flat world. Right occipitoparietal damage can lead to deficits in binocular convergence. Traumatic brain injury leads to loss of fusion in stereopsis, and agnosia, loss of relative disparity. But the most common cause is amblyopia and strabismus. Amblyopia is a developmental disorder of vision. It's attributed to a history of abnormal visual experience early in life during the sensitive period, and it's a terrific model for studying plasticity in humans. And the idea that's sort of driven my work over the last 25 years or so is illustrated in this cartoon showing the development of visual function. So visual function is developing over time. And down here, as function develops, Entwicklungspotential, or the potential for change or plasticity, is waning. And what we've been interested in is if there's some obstacle to normal development here when there's a high level of plasticity, but treatment is delayed till much later when plasticity is diminished, can you recover vision? Is there plasticity beyond the sensitive period? And the kind of obstacles that I have in mind are strabismus, a turned eye, or anisometropia, where the two eyes have very different refractive errors, and so development goes with one eye having a clear focused image and the other eye having a blurry image, and more rarely form deprivation, such as a unilateral cataract. So amblyopia is sometimes called by the misnomer lazy eye. It's characterized by a reduced visual acuity in an otherwise normal eye. It has an onset early in life, and it's always associated with a history of abnormal binocular vision. And it occurs because the two eyes do not get correlated input during a sensitive period of development, either because the two eyes are looking at different parts of the world because of strabismus, or because one eye has a blurred image relative to the other eye. It's the most common cause of visual loss aside from refractive error in infants and children, a prevalence of about 3%. And it's typically defined as a reduction in visual acuity, but there are many other deficits, including contrast sensitivity, vernier acuity, and for the purpose of this talk, stereo acuity. So why does stereopsis matter in amblyopic patients? Well, one is that they often have visuomotor deficits and impaired visual feedback control of their movements. And these are thought to be due to the impaired stereopsis rather than visual acuity loss or impaired vergence control. Loss of stereopsis may also result in unstable gait, and for children, difficulty in playing sports, and it may limit employment opportunities later in life, such as if you want to be a pilot in the Israeli Air Force, you have to have good stereopsis. Now, Sue Berry was a neuroscientist who was strabismic much of her life and then regained stereopsis through training. And she writes that a person who has normal binocular vision cannot view the world as a stereo-blind individual, even when they close one eye. Their brain will use a lifetime of stereo vision experiences to fill in the missing stereo information. So this brings up a paradox. A normal binocular viewer cannot imagine vision without stereopsis, and a stereo-blind viewer cannot imagine vision with stereopsis. So can one learn to see in depth beyond the sensitive period? Brock wrote, it must be repeated here that before stereopsis is actually experienced by the patient, there's nothing one can do or say which will adequately explain to him the actual experience, the actual sensation experience. Once the patient has experienced this new sensation, he's only too anxious to use it again and again. Well, in people with normal vision, stereopsis can be improved by training. So here we have a setup where each eye sees these two images. They're combined binocularly in a stereoscope so that you see one. And the idea is that the person has to decide whether the central patch is in front or behind the other patches around here. And over the course of about 14 sessions of 500 trials each session, you can see that their stereo threshold improves from about 30 arc seconds down to about 10, about a factor of 2.5 to 3 improvement. But what about people with amblyopia? Well, it's a little embarrassing to say, but just over 20 years ago, Uri and I showed for the first time that individuals with amblyopia can improve their vision by practice. So we had people practice a vernier acuity task. This is a task that they do with their amblyopic eye, where they have to decide whether this line is higher or lower than that line. They're briefly flashed. They're quite low contrast. This is data on one subject, and you can see that his vernier threshold improves quite rapidly over the course of about 50 blocks of 125 trials per block, so something like 6,000 trials. And this particular subject wanted to be a policeman in Dallas. That was his life's ambition. And to be a policeman in Dallas, you have to have 20/20 vision in each eye because you have to be able to do this. So we tracked his visual acuity, and that's shown by the green spots, green dots here in the right-hand axis. So his visual acuity at the beginning was 2.2 arc minutes, or 20/44. And you can see over the course of the training, it improved to 20/20, and he went off to Dallas. What about improving stereopsis? Here's results on a 65-year-old anisometropic grandmother. So she did the same task as I showed you for stereo in normal subjects. When she started, she could only see a very coarse, low spatial frequency target in stereo with a threshold of 3,000 seconds. Remember, the normals were at about 30. And she couldn't do any finer spatial frequencies. So we trained her on the vernier task that I just showed you that the policeman did. And after that, her stereo got a little better. And now she was able to also do it with a slightly finer 2.5 cycle per degree patch. We had her come in to the lab for many, many, many sessions, 120 kilo trials, and eventually she improved by about a log unit down to almost 300 seconds. Still not normal, but a factor of 10 improvement. And now she's able to do it at even high spatial frequency with small patches. It turns out monkeys can do this as well. Professor Chino, who's talking later today, had monkeys reared with prisms for the two eyes, causing them to be strabismic. And this is normal monkey practicing a stereo task, and these are 3 of the prism-reared monkeys who also show improvements on the order of 7-fold. But what Professor Chino can do that I can't do on my humans is, in these monkeys, he could look at their neural responses in the visual cortex, and he found essentially no effective training in area V1, the first visual area, but a roughly 2-fold improvement in area V2, and so perhaps there's even further improvement at higher levels. Now, the bigger challenge is people who have strabismus, that have a turned eye, and so they have 0 stereopsis, because if you try to train them on a perceptual learning task, they get very frustrated and they will want to kill you. But we were quite inspired by this report by Bruce Bridgman, who went to see Hugo. Bridgman was a vision scientist, actually, who had strabismus most of his life, had poor stereopsis, went to see the movie Hugo with his grandchildren, and he rented the headset, thinking he wouldn't see anything in depth. And to his amazement, he did, but he thought, well, they have very large disparities. And the movie makers took a lot of trouble to make the 2-dimensional depth cues line up with the 3-dimensional cues. But then when he walked out of the movie theater, he retained stereopsis. He saw the world in depth. He saw things popping out that he couldn't see before. So our idea was to try to use 2-dimensional depth cues, such as the perspective in this Renaissance painting, as training wheels for recovering 3D depth in individuals who had poor or no stereopsis. So the question we asked is, can you use the rich 2-dimensional depth cues as a scaffold for recovering stereopsis? So we combined monocular texture cues, 2-dimensional depth cues, with stereoscopic cues, and the hypothesis was that if the observer could learn the correlations between monocular and disparity cues, they could learn to give greater weight to stereo. So this is done with virtual reality, and what we did is to develop a bug squashing game. So the idea is that there is a virtual bug, it's a dicoptic bug, on a slanted surface, and the surface is slanted in depth, at different depths. And the slant can be determined either by linear perspective cues or by stereo cues. What the observer has to do in the game is squash the bug on the surface by aligning the slant of a cylinder with the slant of the surface. And so if they get it right, it explodes and they get points, and if they get it wrong, the bug just kind of scurries away. And we use a motion tracking system to capture the slant of the cylinder in real time so we can track their performance. This is, if it works. Nope. Okay. So the idea is that there's a dicoptic bug. Parts of the bug are seen by one eye, other parts are seen by the other eye, so that when you view it with both eyes, you see the entire bug. And we adjust the 2 halves of the bug so that they appear to the subject equal. That is, the apparent contrast is equal. And so we use monocular cues from the distortions of the regular grid patterns as one way of defining the slant in depth, and we also use disparity cues, and those cues could be either consistent or inconsistent. So over trials, over sessions, about 30 to 40 sessions, these are normal observers. You can see that their hit rate, the accuracy with which they make the judgment, improves for both consistent cues, inconsistent cues, and pure disparity cues. And these are mean data on 11 stereo blind or stereo deficient subjects. And like the normal subjects, they get better too. Not quite as good with the pure disparity stimuli, but still quite a bit better. A simple model which we use to fit the data, that these lines, has 4 parameters: monocular Q noise, stereoscopic Q noise, motor noise, and bias. And what you can see is that the monocular Q noise gets reduced, that is, it becomes more reliable, but there's a huge reduction in the stereoscopic Q noise. That is, the information becomes much more reliable according to this model. And in fact, we can measure to what extent they use these cues and what weight they give them by essentially looking at regressing the slant of the cylinder against the slant depicted by the texture and the slant depicted by the disparity. And what you can see is that for normal subjects, there is an increase in the relative weighting of the stereo information as they go through practice. In the stereo deficient observers, they start off giving very little weight to stereoscopic information. And over time, that increases substantially and significantly. This is the evolution of stereo weighting, reweighting in one subject, our favorite subject we call S1. You can see he starts off very low, and over time he winds up weighting the stereo information equally to the monocular information. So, and this basically just summarizes data for all our subjects. This is pre-training relative stereo weight, post-training weight, and this is a unity line, so anything above the line is an increase in weighting of the stereo. This is S1, starts off very low, ends up with high weighting. The FU is follow-up, not what you're thinking. And you can see that 2 months after stopping the training, it's still pretty much, it's not exactly retained, but it's mostly retained, and that's true for many of the other subjects as well. So 8 of the 11 observers actually put more reliance on the stereo information following the training. And importantly, their stereo acuity improved. So this is stereo acuity before training, after training, and now, with apologies, any improvement in stereo after training is shown by points below the line. So here's S1, who started off at 200 arc seconds, and after training is at 20 arc seconds, and that is retained. And so 6 of those 8 subjects actually showed significant improvements in stereo acuity. And most importantly, perhaps, the change in stereo weighting predicts the improvement in stereo acuity. So this is the change in relative stereo weight. This is the change in stereo acuity, and you can see for 2 different tests, a very high correlation. So reduced stereopsis, it turns out to be the most common deficit associated with amblyopia under ordinary binocular viewing conditions. Impaired stereopsis may impact visuomotor tasks, playing sports and locomoting safely in adults. And recovery of at least some degree of stereopsis in patients with amblyopia, even well beyond the critical period, is possible. And this recovery seems to be accomplished by upweighting reliance on stereoscopic information. Many brain areas, as I showed you, are activated by binocular disparity, and we're now studying where the neural changes occur. Now, one of the exciting things is in the olden days, to train stereopsis, eye doctors and orthoptists use something like this. It's a mirror stereoscope, where there are mirrors that separate the images to the 2 eyes, and you put slides in there. But today we have many advances, technological advances in virtual reality, such as the Oculus Rift or the Microsoft HoloLens. And so we think the future is here, because it will be easy to actually have patients take these devices home. So these are the collaborators on this project, and I want to thank you for your attention.